Welcome to Unit 1.6, in which we are going to discuss the VM emulator. The VM emulator is a very versatile and useful tool that will come to play in many stages during this course, beginning with the present module. So let me start by placing the VM emulator in the larger scheme of what we are doing. Now, to remind you, our overall purpose is to translate high-level programs written, say, in the Jack language into machine language. And in order to do it, we use a two-stage compilation model. So in the first stage, we compile from the high level to VM code. And in the second stage, we have to somehow execute this VM code on the target platform. One way to do it is to translate the VM code into machine language and then load the binary code into the target platform, in this case, the heck computer, and execute it. And there's also a shortcut which enables you to run the VM code as is. And you can do this using the VM emulator. So the VM emulator is a high-level program. It's written in Java, in our case. And you can run this VM emulator on any computer, including your own PC. And indeed, if you downloaded the Nano2Tetris software suite, you have on your computer the VM emulator that I'm going to discuss throughout this unit. People use the VM emulator for various purposes. First of all, it provides the most natural and simplest way to execute compiled Jack programs. And even if this program has all sorts of visual effects like bouncing balls and playing Tetris and so on, you're going to get all these goodies in the VM emulator environment. And you can also test the programs in a systematic way using supplied test scripts, which is also a nice feature of this tool. And also, people use the VM emulator in order to understand the VM abstraction. If you want to single step through a VM program and observe the impact of every push and pop command and so on the virtual segments and the stack, the VM emulator provides a very friendly environment to do just that. And finally, the VM emulator also gives you a glimpse into how the VM abstraction is actually being hosted on the host platform. And this will become clearer as we go on in this unit. So here's the VM emulator in all its glory to do just that. And finally, the VM emulator also gives you a glimpse into how the VM abstraction is actually being hosted on the host platform. And this will become clearer as we go on in this unit. So here's the VM emulator in all its glory. And beginning with the left-hand side, we see some VM code loaded into the VM simulator environment. This is the code which presumably is now running. And we also see a set of controls that enables us to control this code, single step through it, fast forward, increase the speed in which the code executes, and so on. Here we see the output that the program presumably generates, in this case, some bouncing ball. And the VM emulator is built in such a way that this pane in which the output is displayed is kind of a multi-purpose window, and it can serve the user, you, as a means with which you can look into various files, like the output file that your script is generating, the script file, compare file, and we'll illustrate all these as we go along. Then we can take a look at the stack and see how it changes in response to various push and pop commands. And finally, we can also look at the virtual memory segments and see how they are being affected by the VM program. There are a few more controls and features of the VM emulator that I will discuss later on. So here's an example of what we do in general with this tool. We take some piece of code, we load it into the VM emulator, and then there are a few things that we have to watch for when the code is executing. First of all, we have to understand, or we view this VM emulator as some sort of a hands-on laboratory. So we can look at the code and see how it impacts the stack and the virtual memory segments. And by doing so, we will understand better how the VM abstraction is working. And we can also look at the right-hand side of the VM emulator's GUI. And if we take a look at this area, we will see how the VM abstraction is actually being realized on the host platform, on the RAM of the host computer. So we get sort of a dual view of both the abstraction and its implementation. And it's very instructive and powerful because you can really see how the virtual machine works in two different layers of interest. Now, the next topic that I'd like to discuss is the notion of test script, which is central to Project 7 that you will have to do in the context of this module. So here's a test script. It's just a plain text file, typically supplied by us. And it's just a plain that you will have to do in the context of this module. So here's a test script. It's just a plain text file, typically supplied by us. And the first thing in this test script is typically a load command, which tells the simulator to load a VM file into the simulator's environment so that we can execute and test it. Now, these VM files are typically supplied by us, or you can write files of your own, but if you want to do it, you have to use an external text editor and save it with some file name .vm, and then you can use a load command like this one in order to load it into the simulator's environment. You can also load it interactively, but here we're discussing the notion of a test script, which does everything kind of batch style. The next command in a test script typically defines an output file into which the test script is going to write some values during the execution of the program. So for now, we have an empty output file. Then typically, the supplied test scripts also load a compare file, which is supplied by us. And the compare file looks like different compare files look differently. Typically, it lists the names of several selected containers, like selected areas in the RAM or in the memory segments and so on. So you get the names of the containers and the current values, or the values that the script expects to see during the program's execution. Now, what we'll see next is some output formatting command. And the good news is that you don't really have to fully understand all the syntax of these test scripts, because we provide all these test scripts. They are written in what we call TDL, Testing Description Language. It's not really part of the course, and we don't have to delve into it. We have enough challenges elsewhere. So once again, we just have to understand the spirit of what's going on. And the next thing that we see in the test script is a loop that instructs the simulator to execute the program, one VM command at a time. And in this particular case, in the case of the basic test.vm file, we have 25 instructions, so 25 iterations will be enough to carry out the execution of this code. And enough to a test script is a loop that instructs the simulator to execute the program, one VM command at a time. And in this particular case, in the case of the basic test.vm file, we have 25 instructions, so 25 iterations will be enough to carry out the execution of this code. And finally, in this particular test script, we see that we have only one output command at the end of the script. And when the simulator executes this command, it will print to the output file all the variables that were defined in the output list command in the preamble of the script. Now, here's the deal. If the generated output file is the same as the supplied compare file, we say that the test is successful, and the simulator will give you a positive message that the test has completed successfully. If, however, there is some discrepancy, the simulation stops and you get an error message. So that's the basic idea of using a test script. Now, as it turns out, because we split the development of the VM translator into two stages, Project 7 and Project 8, in Project 7, there are some missing elements that have to be dealt with. In particular, the programs that we run in Project 7 are not really programs. They are, you can think about them as a sequence of instructions, and what is missing in these programs, or what is missing in these sequences in order to make them programs, are what I call the function and return envelope. And the function and return commands later on in Project 8 will cause the VM implementation to initialize the various segments that the method or the function expects to use. The local segment, the argument segment, the this, that, and so on. So in Project 7, these segments are not initialized anywhere, and therefore someone has to take care of these initializations, and we do it using the test script. So as you see, we write a set of commands. I mean, once again, these test scripts are supplied to you by us. And what we did is we added batches of commands that initialize the virtual segments manually and anchors them on selected areas in the RAM. So once we execute this setup stage in the test script, the VM code will run properly. So what I'd like to do next is give you a more detailed example of the VM emulator in action. I would like to illustrate the working of the VM emulator in the context of Project 7, because in this particular project, you're required to handle several VM files, and therefore I think it makes sense to see how this tool works in the context of the project that you have to do yourself. So what we have here is my NAND to Tetris folder, and let me go into projects, and within projects I select Project 7, and within these two folders I'm going to select memory access, and within memory access let us go into basic test. And I see that I have 4 files here. The first one is a compare file, the second one is a test script, the third one is a VM code, and the fourth one is yet another test script. So it's interesting, why do we have 2 test scripts here? Well, this is something that I will explain later on. So let me bring up my VM emulator and proceed to load the VM file that we have in front of us. So I go to basic test, and I see that I have a basic test.vm. I load it, and let's see, it looks like we have 24 commands, actually 25, including command number 0. So let's start executing it by single stepping through the code. So the first command is push 10, and indeed we see that we have 10 in the stack, so things look good. Pop local 0, let's execute it. Oops, I got an error message, out of segment space. Well, the problem is that in this particular VM file, we don't have function declaration command at the beginning of the code, and therefore no one told the simulator, so to speak, that it has to allocate memory space for the virtual memory segments, the static, local, argument, and so on, and therefore we ran into this problem. So the quick and easy way to handle this challenge of anchoring the memory segments in the RAM is to use test scripts. So instead of loading the VM code, we always recommend to load instead the test script if such is available. So let's do that. And we have 2 test scripts here. We'll choose this one, the vme.tst. We load it. And it seems like nothing happened. Well, that's because we have a little bug in the GUI. If you click this pane here, you will see the test script in all its glory. And now we can begin executing it. So I'm going to single step as I did before. So let's click run. And we see that several commands got executed within the test script. And indeed, the test script always executes, or the simulator always executes all the test script commands up to a semicolon. So comma is considered a microstep, a semicolon is considered the end of the step, and therefore, when we did single step, we told the simulator to execute the first 4 commands. The first command was load basic test VM, so the simulator essentially reloaded the file that already happened to be in the program pane, and it's very good that we reload it because normally, we may want to do some debugging in the middle, so it's always good to sort of start from fresh. And then the test script defined an output file, used a certain compare file, and so on. Well, all this is not terribly important to understand because we don't expect you to delve into the details of the code of the test script. You just have to understand the spirit of what is going on. So let me click the single step again. And we see that we executed all these commands in the first VM step. So indeed, we did a push constant 10, and we see that the stack contains 10. Very nice indeed. We'll execute another command, and we see that the command that we executed was pop local 0, and indeed, local 0 now contains 10. So let me push 21 and push 22. Pop argument 2. Indeed, we see that argument 2 now contains 22. Very nice. Push 36. Pop this 6. We see that this 6 now contains 5. The stack contains 42 and 40 point. If I want, I can also take a look at the host platform and see how what I did so far is being reflected in the underlying host platform, which happens to be the hack computer. So I'm going to shift my attention to the host RAM, and I see that the stack pointer is 258. Now this makes sense because according to the standard VM mapping on the hack platform, the stack should begin at 256, and indeed we had a command in the test script that said set SP to 256. So the stack pointer was initialized to 256, and we now have 2 values in the stack, and therefore the stack pointer should be 256 plus 2, which is 258. But just to make sure, I can also scroll down the RAM here. 256 should not be too far away. Indeed, here it is, and lo and behold, I now see how the stack is hosted in the host RAM. It's right here, 42, 45, and stack pointer presumably, not presumably, I know that stack pointer points at 258. So things look nice as far as the stack is concerned, and I can explore some other things. For example, it's interesting to see where the argument segment is stored. Well, arg is 400, so let me use this binocular control here, and enter 400. And this takes me to address 400 in the RAM, and I see that what I have here is 0, 21, 22, which is the same as what we have here. So on the left, we have the abstract rendition of the argument segment, and on the right, we have a glimpse into how this abstraction is actually implemented on the host platform. All right, going back to the code, I can continue to single step through it, but this becomes a little bit tedious, so I can also fast forward. And if this is not fast enough to my liking, and I can also use the slider to make it faster. Now, when we fast forward, we essentially carry out a succession of single-step events. And in every one of these single steps, we carry out the test script commands up to the next semicolon. So basically, we went through this loop here, and we did 25 iterations. And 25 iterations were enough because in this particular program, we have only 25 instructions. Now, how do we know that the program actually did what it's supposed to be doing? Well, typically computer programs are designed to carry out something very concrete, like bouncing a ball on the screen or staging a Tetris game or deciding if a given number is a prime. And therefore, the testing of these programs in many cases is relatively straightforward. But in this particular program and in other programs in Project 7, some of the code is rather obscure because it doesn't have some global purpose in mind, but rather it is written in order to test, or I should say unit test, specific VM operations on the stack and on some of the memory segments. And therefore, if you want to test this program at the VM level, then you can either follow each instruction in isolation, interactively, as we did before in this demo, or you can let the supplied test script carry out the test on its own, so to speak. And in order to do this, you run the test script until it ends, and then if you get the nice message, end of script comparison ended successfully, you can conclude that the program has passed the mandated test. Now, the logic here is that when you execute a script file, whenever the simulator encounters an output command within the script, it compares the result of this output to the current line in the compare file. And if the output line and the compare file line are in agreement throughout the execution of the script, then at the end, you're going to get this nice positive comparison ended successfully message. If there is some discrepancy along the way, the simulation is going to stop and you're going to get an error message. Now, if you want to get into the details of this process, you can go to this control here and take a look, for example, at the output file that this particular script has generated. Now, in this script, we had only one output command at the very end of the script, and indeed, we have only one line of output. And this line displays the values of some select words from the memory that, taken together, can help you ascertain that the program has done what it was supposed to do. So we can look at the output, we can also look at the compare file, and we know that the compare file will be the same as the output, because otherwise, we would not have gotten this nice completion or program completion message. And once again, this is sort of the standard way to test the program using the supplied test script. So this is the end of our VM emulator demo. There are a few bells and whistles in the features of the emulator software that I decided not to illustrate because we don't need them at the current level. We will need them when we start working on Project 8, the next project in our NAND to Tetris journey. So to recap, the VM emulator has several purposes. First of all, it allows us to run and test high-level programs or compiled JAK programs. And also, it's a hands-on lab that allows us to delve into and understand both the VM abstraction and its implementation. So I hope that you enjoyed this basic introduction to the VM emulator. And in the next unit, we're going to talk about the VM implementation on the Hack platform. In this unit, we're going to discuss how we implement the VM abstraction that we introduced so far on one specific hardware platform, which is the Hack computer. Now, to begin with, I would like to refresh your memory about what is the VM translator to begin with. Well, the VM translator is a program written in some high-level language like Java or Python, and or any other language, and the program gets as input another program written in VM code, VM commands like push, pop, and so on, and then it parses this file, it parses each individual command, it breaks it into various lexical elements like push, constant, and the integer 2, and then using these lexical elements, it re-expresses these commands
Sería como un assembler, ¿no?
using assembly commands of the target platform, which in our case is Hack, and therefore we use the Hack assembly language. Now, notice that what we have on the right is the output file, and one thing that I recommend that you do when you get to develop this translator is that whenever you translate a particular command, you write a comment that shows this command. This will help you debug the output of your VM translator down the road. Now, naturally, each VM command, which is high level in this context, is going to be translated into several assembly commands, as we saw when we talked about translation in previous units. Now, if you want to write a general purpose program that can translate any given text in the French language into the Spanish language, it really helps if you first know these two languages, French and Spanish. Likewise, if you want to write a VM translator, you have to be competent in both the source language, the target language, and you also have to know something about where should we place the various virtual data structures like the stack and the segments on the host computer, and how are we going to translate the high-level commands into the assembly commands. So with that in mind, the source language that we have to deal with is the VM language, consisting of arithmetic, logical, and memory access commands, as well as branching commands and function commands. But in this particular project, in Project 7, we're going to focus only on the arithmetic, logical, and memory access commands. And in the next project, that will be the centerpiece of the next module, Project 8, we will complete the picture and handle also the branching and the function commands. The target of our translation is going to be symbolic Hack language, and we went through this language in module 0, and this language consists of two major commands, the A command and the C command, and that's it. That's all you need in order to translate your VM programs into assembly. Now, another thing that we need to know is what is sometimes called the standard VM mapping on the target platform. Now, let me explain what I mean by, let me first show you the standard mapping, and then we'll discuss why we actually need it. So basically, we have to make two decisions: how to map the VM's data structures on the host RAM, and also how to express the commands in the host language. Now, the standard mapping gives you all sorts of information or conventions on how we propose that you achieve this mapping. Because think about it, if I tell you to implement a VM translator, basically you're free to do whatever you want. I can tell you, here's the RAM, do whatever you want with it. However, it is convenient and customary to propose a certain standard mapping that will ensure two things. First of all, if you agree to put the various segments in where you advise and where we advise to put it in the RAM, then you're going to conform to generally accepted standards that are also accepted by developers of other software tools that run on the same computer. So if everyone respects the same rules, these programs will not collide in the memory. And also, if you commit yourself to a certain mapping on the RAM, then we can write all sorts of test programs that also make similar assumptions. And by doing this, the team that tests the software can be another team other than that actually develop the software, which always is recommended in order to perform objective testing. So that's the purpose of the standard mapping. So here's the standard mapping of the VM on the Hack computer. Basically, I repeat things that we discussed in previous units, but I just wanted to put them in one slide so you'll have all of it in one place. We use the first 5 words for the segment pointers. Then the next 8 words serve as the implementation of the temp segment. Then we have several, I think 3 general purpose registers. Then we have 250 or 240 something static variables. And the rest of the memory, all the way up to 2K, is going to serve as the place where we're going to host or store the stack of the virtual machine. So all these segments that we mentioned before are going to be mapped onto this RAM using the logic that you see in this slide. I don't want to read all this. It's something that you can go through yourself. And if we want to achieve this mapping, then when we write the VM translator, we have to use certain symbols. Once again, certain agreed upon symbols when we generate the assembly code that realizes the VM code on Hack. So in particular, we're going to use SP as a special label that stands for the stack pointer. We're going to use LCL, ARG, this and that as the segment pointers of the respective memory segments. We're going to use R13, R14, R15 whenever we need to use some special purpose, some general purpose registers. And finally, if you recall, we described in the previous units how we're going to use special labels, specially generated labels, in order to represent static variables. The file name dot some running index will stand for the static variable that has the same running index. So your VM translator, when you write it in order to generate assembly code, your code is going to use these symbols. You have to be responsible for writing code that generates these labels and uses them judiciously in order to implement, in order to realize the mapping that we just described. Now, finally, I would like to mention that in Project 8, in which we're going to implement the remaining VM commands that we haven't implemented here, we're going to extend this mapping somewhat and add a few more conventions to it. So with that, this has been our unit on how to map the VM translator or the virtual machine on the host RAM and the host computer. And now we'll finally come to discuss how to actually build this program using a high-level language. All right, so let us begin to discuss how to actually build a VM translator using some high-level language. Well, to begin with, I'd like to remind you, as I did in the previous unit, what the VM translator is all about. It's a program that reads a given text file, which contains VM commands, and produces from it another text file that contains assembly commands. So, for example, the VM translator can, begins to parse this particular command, the push constant 17, breaks it into its lexical elements, and builds from it the output at 17, d equals a, and so on and so forth. Then it moves on to the next command, it parses it also, and then it generates the assembly code that realizes push local 2 on the target platform. Then it does the same with add. It reads add, and it does some, hocus pocus in assembly that it also, and then it generates the assembly code that realizes push local 2 on the target platform. Then it does the same with add. It reads add, and it does some hocus pocus in assembly that causes a stack-oriented add operation. Pop local 2 is translated into a set of assembly commands that represent pop local 2, and so on and so forth until the end of the input file. So that's what the VM translator is all about. What I would like to do next is show you how this VM translator will be used once you end up writing it. So let's assume that we've implemented a VM translator and we want to apply it to a particular VM program that we wrote before, either a test program or some real program that we wrote in one way or another. And now we seek to translate this program into assembly code. How do we do it? Well, on my computer, I open a terminal window. If this were Windows, I would probably do the same using the command prompt. And then, because I wrote this VM translator using Java, I apply the Java runtime system to my VM translator, and I supply the name of the source program as a parameter to my VM translator. And once the translation has ended, if I will look again into the current directory, I will see that a new file was created. This new file has the same name as my input file, but it has a different extension, an ASM extension. And presumably, this file contains the assembly code, which is the translation of the source VM code. Now, obviously, the next thing that I would do is I would take a very eager look into this ASM file using some plain text editor, and I would like to try to make sure that the code that my VM translator generated is indeed valid. But that's a separate story. We'll discuss it later when we talk about compare files and so on. So now that we've seen this VM translator in action, we are ready to talk about how to actually build the VM translator. Now, it really all depends on which implementation language you're going to use, and it can be Java or Python, for example. And whichever language you will use, we recommend a certain software architecture which we think is appropriate for this project. So we propose to develop 3 standalone modules, if you will, or in the world of Java, this will be called 3 different classes: a parser class, a code writer class, and a main class. And the main class is just a surrogate name for the class that we saw before, which will be called VM translator. So the main class, the VM translator, has one input, which is a file name .vm, and it generates as output a file name .asm, as we saw in the demo that I previously showed you. Now, how does this main class operate? Well, the logic of this main class is that it will have some main method that does the following. First of all, it constructs a parser in order to handle the input file, and we'll discuss this parser later on. Then it constructs a code writer to handle the generation of the code that we have to output, and we'll discuss this code writer later as well. And then once we have these 2 objects set up, we can march through the input file, through filename.vm, and handle each row in this file separately. For each of these rows, which represents a VM command, we can parse this row or line using our parser, using our parser functionality. And once we parse this line into its constituent VM elements, we can pass this information to the code writer in order to generate the appropriate code in assembly that we will later put together and write to the output file. So that's the general logic of the main class called VM translator, and that's what you have to implement when you develop this particular class. Now, I'd like to point out that as you see, in order to implement this class, you have to know how to handle text files in your implementation language. So, for example, if you use Java, you have to know how to open a text file, how to read the next line from this file. You have to know how to open a file for output. You have to know how to write strings into this output file, and so on. And all of this, obviously is not part of this course. It is on you. We assume that you know how to handle files in your implementation language. And if you don't, maybe you want to take a break from this course and spend a few hours on learning how to do this using Java, Python, or whatever language you use for this project. All right, so here's the API of the 3 modules, actually the 2 remaining modules, the parser and the code writer. The parser, once again, handles the parsing of a single VM file. It reads a VM command, it breaks it into its individual elements, and it passes this information to the code writer. And in the process, it also removes all the white space and the comments from the source file. So it doesn't really remove them, it simply ignores them. It goes over the white space and focuses only on the real essence of the file, which are the commands themselves. So, as usual, a module consists of a set of methods and constructors, and here's what we propose to do. We propose to, first of all, write a constructor whose job is to open the input file for processing. So it receives as a parameter a string, which is the name of the file, and it goes on to open it. Then there's this method, has more commands, which is a Boolean, and it simply tells you if there are more commands to process in the input file. If there are more commands to process, if has more commands is true, then we can do an advance. And by advance, we take the current command, the command that we are now looking at in the file, and we turn it into what we call the current command within our program. And we're going to refer to this current command in many different places. So moving along, the command type method looks at the current command and decides if this command is an arithmetic logical command, or a push, or a pop, or a label, or a goto, and so on and so forth. And for every one of these command types, the command type method returns a constant. And once again, other methods in our API will use this constant down the road. Then there are 2 methods called argv1 and arg2, which return the arguments of the current command, and you can read the specification to see exactly what these methods have to return. So this completes the description of the parser API. Moving along, here's the code writer API. This class, or this module, is responsible for generating the assembly code from the parsed commands. It also has a constructor, and the constructor opens the output file for processing and gets ready to write onto this file. Then there's a write arithmetic method, which is responsible for writing the assembly code that implements the command, which is the parameter of this method. And this is where most of your work will be invested, because based on which command you're currently processing, you have to write assembly code, and there are several such commands. So there's some significant work to be done with this particular method. And the next method, write push pop, is also a heavyweight method, because based on whether you have a push, a pop, and the segment and the index, you have to generate assembly code that implements this particular command. And finally, there's a close method that simply closes the output file, and that's the end of the story. So this completes the API of our basic VM translator. And more routines will be added to this API in the next project where we handle the rest of the VM language. Now, obviously, what we gave here is what we think is a good architecture for the VM translator, and you're welcome to add to your own code more private methods, which are not exposed to the outside, and use these private methods to make your code more manageable, elegant, and readable. And with that, I want to remind you what is the big picture of what we're doing. We have described the implementation of a VM translator that can handle the arithmetic, logical, and the memory access commands. And what remains to be done is to complete this translator in the next project to handle also the branching commands and the function commands. So that's the end of this module, and moving along, the next module will describe how you actually have to do it and submit the project. In this unit, we discuss Project 7, in which we build the first part of our VM translator. Now, since this is the first project in the course, I'd like to say a few words about the big picture. And what you see here is the overall NAND to Tetris journey, which starts, if you think about it top-down, it starts with some human thought or some fantasies about developing, let's say, a Tetris game or a Pong game or something like this. And then you go through several stages of construction until you end up with a program that actually runs on a real computer. Now, to remind you, we decided to divide this overall journey into two different parts, two different courses. And in NAND to Tetris Part 1, we've built the hardware platform, which is the host computer on which we can actually execute programs. In this course, in part 2, we build the elaborate software hierarchy that sits on top of the host hardware platform and enables us to write programs in a high-level language like Jack or Java or Python, and then translate them all the way down into machine language, generating code that can actually execute on the platform that we built in part 1. Now, we decided to split this overall journey into 6 standalone projects, which are numbered Project 7 all the way up to Project 12. And we also have Project 0, which is kind of optional and was the focus of the first module of the course. And in this particular module, we're going to focus on Project 7, in which we build the first stage of a full-blown VM translator that can translate programs from VM code to machine language. And I also listed Project 0 because we're going to use some tools that come to play in Project 0, and they will serve us in Project 7 as well. Now, to remind you, the VM code is written in the VM language. And the VM language consists of 4 categories of commands, of which in Project 7, we're going to focus only on the first 2. So we're going to develop a basic VM translator that is capable of translating VM programs that include arithmetic, logical, and memory access commands into machine language. And in the next project, in Project 8, we're going to deal with the rest of the VM language and complete the picture of building full-blown VM translator. So here's an example of a VM program, which is stored in some VM file. It is actually a set or a sequence of VM commands. And the goal of Project 7 is to write a program in a language like Java or Python, a program which is called the VM translator, that goes through this input file and translates it into assembly code. So here's the translation of the first VM command. And then we continue to go through the input file, and for each VM command, we provide or we write the translation of this command into the output ASM file. And notice that just a little detail that I recommend that your VM translator will always emit a comment that specifies which command it is now translating. If you do this, then debugging will be much easier, because when you read the produced assembly file, you can sort of see and relate the assembly code to the commands that generated it. So that's the overall goal. Now the question is, how do you test the translation? How can you tell or ascertain that the VM translator actually generates legible machine-level code? Well, you can take this code, the code that was generated, and load it into the target platform, in our case, the hack computer, run it, and convince yourself that the code is doing what the source code intended to do. So going back to the overall picture, we can once again take the code, load it into the machine level, and run it. Now, if you didn't take NAND to Tetris Part 1, and also if you did take it, there's an alternative way of doing it. Instead of using the actual hack computer, we can use a supplied CPU emulator that can run hack programs as is and do exactly what the host platform would do for real. And if you use the CPU emulator, you can run it on any computer, including your own PC. And indeed, if you downloaded the Nano Tetris software suite, you have this program available to you, and we use it actually in Project Zero, and that's why I listed Project Zero as an element of Project 7 as well. So we can use the CPU emulator to test that the resulting code does what it's supposed to do. All right, now I'd like to go through our development plan, which is a little bit elaborate, and explain what we have to do in every step of the way. So first of all, we supply 5 VM programs, and each one of them is designed to test some specific features of the VM translator that you are building in Project 7. Every one of these programs is stored in a separate directory, so there are 5 directories that have the same name as the name of the program. And here's an example of one of these directories called basic test. Now, the most important file in this basic test directory is the VM program itself. That's the program that we have to translate. And the other files provide some other purposes that I'll explain. Is main directories that have the same name as the name of the program. And here's an example of one of these directories called basic test. Now, the most important file in this basic test directory is the VM program itself. That's the program that we have to translate. And the other files provide some other purposes that I'll explain later on. So here's the contract. Your job is to write a VM to HACK translator which conforms to the standard VM to HACK mapping that we described in Unit 1.7. Now, you have to use the VM translator in order to translate every one of the 5 VM files that we supplied in this project. And for every one of these translations, you have to generate an assembly program. And then when you execute the resulting assembly program on the VM emulator, the output file that our script is going to produce from your code has to be the same as the supplied compare file. If this is the case, you pass the test and you can go on to translate the next VM program and go through the same routine. So let me go through the exact steps that I recommend that you go through when you test every one of these 5 programs. Well, first of all, there's an optional stage that I recommend that you go through, in which you take this VM program and you play with it in the VM emulator. And I recommend that you do it in order to get acquainted with the VM program and understand what it is designed for, and you play with it in the VM emulator. And I recommend that you do it in order to get acquainted with the VM program and understand what it is designed to do. Now, it's not really directly relevant to this project because this project translates the program into assembly, and the VM translator doesn't really care what the program is doing. It views it as a translation task from one file to another. However, if you spend a few minutes playing with this program, it will give you a lot of good context for the subsequent translation task. All right, so the next thing that you have to do, once you understand what the VM program is doing, you invoke your VM translator, the program that you wrote, and you translate it into an assembly program, which is stored in a separate ASM file. Now, the next thing that I recommend you do is take this resulting ASM file, load it into some text editor, and convince yourself that the file looks good. After all, this file was generated by your VM translator, and you want to make sure that it generates some legible VM commands. If there's any problem, you have to go back to the VM translator and fix it and repeat this process. Once you've completed this visual inspection, you can load the ASM file into the CPU emulator and proceed to execute it and inspect the results. Unfortunately, the last stage, stage 4, will not work out. And it will not work because the source VM code, as well as the assembly code that your VM translator generated from it, expects to use the stack and the virtual memory segments, and there's nothing in the source code that actually initializes these virtual segments and the stack on the host platform. So instead, you have to load the test script, the supply test script, into the CPU emulator, execute it, inspect the results, and if there's a problem, you can go back to stage 1 and fix your VM translator. If you use the test script instead of the assembly file, the test script will take care of all the required initializations, and then the translated code will actually execute on the CPU emulator correctly. All right, now, you have to use all sorts of tools and resources in this project, and the first thing that you need are the test programs and the compare files. They are available in the project directory on your computer. You have to experiment with the supplied test scripts, with the supplied VM programs. You can do it using the supplied VM emulator. You have to translate these VM programs into assembly. You do it by using your VM translator, the VM translator that you are developing. And then in order to test the resulting code, you use the supplied CPU emulator, as we just explained. And in order to develop the VM translator, you need some resources like a high-level language, Java, Python, and so on. We recommend that you take a look at some tutorials that we provide in the Nano Tetris website, the VM emulator tutorial, the CPU emulator tutorial, and you can also consult Chapter 7 in the Nano Tetris book, The Elements of Computing Systems. So this is an elaborate project, and you have all these tools that will help you complete it successfully. All right, now there's some testing challenges that we have to address, and I actually described them already, so I'd like to summarize them again. The code that we provide in the VM files is missing what I call the function return envelope, and therefore this code does not initialize the stack and the VM segments on the host platform. So these missing items will be supplied in or completed in Project 8, and for now we use a test script that plugs these holes manually. So the test script starts with the usual preamble commands that we don't have to fully understand. It's not, once again, part of the course. Then we have a set of commands that anchor the virtual memory segments and the stack on the host RAM, and then we have a loop that actually executes the resulting machine level code. So we see that we use these commands in order to manually do what Project 8 will do automatically when we get to work on it in the next module. All right, what I'd like to do next is to recap and go through everything that I said so far in the context of actually using the tools that you have to use in Project 7. So this will be done in the next video clip. The purpose of this demo is to walk through the steps that you have to go to when you work on Project 7. So I have here my Nano Tetris folder. Let's go into Project 7. And within Project 7, we'll go into memory access and into basic test. And let me resize the window for better focus. And we see that what we have here are 4 files, a compare file, a test script designed for the CPU emulator. Then we have the VM code that we have to translate into assembly. And finally, we have yet another test script designed for the VM emulator. The star of the process here is basic test.vm. This is the program that we have to translate. So let's take a look at it. Well, we see that we have here a set of VM commands which are designed to carry out various operations on the stack and the virtual segments, constant, local, argument, this, that, and so on. So the challenge that we are facing is to translate this VM code into assembly code and then use the CPU emulator to run the assembly code and ascertain that the resulting code actually carries out what the VM code was supposed to do. And so before we actually go through this translation process and testing process, it makes sense to try to play a little bit with the source code and understand what the source code is designed to do. So let me bring up my VM emulator and load into it the basic test VME test script. And as I said before, I think in one of my demos, there's a little glitch in the output GUI. So sometimes you have to click the output pane in order to see or reveal its contents. And so here's the test script, and we can begin executing it. So let's do a single step through the test script. And we see that several things happen. First of all, the basic test.vm file was loaded into the simulator. And we also see that the test script has created a new output file called basic test.out. I suspect that at this stage, the output file is empty because nothing really happened yet in the execution of the code. And indeed, I can take a look at it. So let's do that. And we see that the output file contains some labels of RAM locations, but no values associated with them. And there are no values because the code did not run yet. So let us now select a fast execution pace and then fast forward through the script. And at this stage, I can kind of sit back and watch what is going on, which is rather difficult because the script runs rather quickly. But now I can go into the virtual segments and the host RAM and explore what happened with this program. And I don't really want to get into this because we already gave quite a detailed demo of the VM emulator. I believe we did it in Unit 1.6. And in fact, we illustrated the VM emulator in the context of this very same program. So there's no need to repeat this material here. Instead, I will minimize now the VM emulator and turn to the next step in the project, which is translating the VM test file into assembly. Now, I wish to remind you that the essence of Project 7 is writing a VM translator, and my VM translator has been written in Java. So in order to use it, I'm going to bring up my terminal window and type Java VM translator. That's the name of my translator program. And then I'm going to supply a parameter, which is the name of the file that I want to translate, which happens to be basic test VM. All right, let's enter this command. And as you see, a new file has been created, and this file is basic test.asm written in the HEC assembly language. Now, it may be interesting to take a look at the contents of this file, so let's do that. So this is the assembly file that was created and generated by my VM translator. Let me scroll downward within this file, and I see that altogether it contains about 200 lines of HEC assembly commands. Now, I remind myself that the original source VM test file contained about, 25 lines of code, and so the translation ratio is about 1 to 8. In other words, every VM command generates, upon translation, generates about, on average, about 8 HEC assembly commands. Now, it may well happen that your VM translator is better written than mine, and therefore it may generate tighter assembly code and achieve a better translation ratio. Now, the next thing I'd like to do is better written than mine, and therefore it may generate tighter assembly code and achieve a better translation ratio. Now, the next thing I'd like to do is test that the generated assembly code is actually correct. In other words, I want to ascertain that this code carries out what the source code sought to do. And in order to do this, I'm going to invoke my CPU emulator. So here's my CPU emulator, into which I'm going to load the supplied basic test.tst script file, this one. And as usual, I will click my output pane in order to reveal its contents. And let's see, I will single step the first batch of scripting commands. And in response, the CPU emulator has loaded the assembly program that was generated by my VM translator into the emulator environment. It's right here. So now I can execute this program and see what happens. So let's click fast forward. And now I can kind of sit back and watch the code that was generated by my program execute. And I see that execution continues because there's nothing that tells it to stop in the code. And at some point, right here, execution has stopped, and the execution stopped because the supplied test script is programmed to execute 600 clock cycles, and therefore at some point it kind of forces the program to stop until execute this assembly program in order to script file, this one. And as usual, I will click my output pane in order to reveal its contents. And let's see, I will single step the first batch of scripting commands. And in response, the CPU emulator has loaded the assembly program that was generated by my VM translator into the emulator environment. To stop in the code. Execution has stopped, and the execution stopped because the supplied test script is programmed to execute 600 clock cycles, and therefore at some point it kind of forces the program to stop. Now, how do I know that the program has run successfully? Well, first of all, I got this very nice message that tells me that I have fulfilled the contract. The translated assembly code has passed the test that was mandated by the supplied test scripts. Now, if you're not sure how to use the CPU emulator, you can go back to Module 0 and look for a unit called, I believe, Low-Level Programming Part 1, and somewhere within this unit you will find a CPU emulator demo that you're welcome to look at, and if you wish, you can also go to the Nano Tetris website, and there you will find a CPU emulator tutorial. So this has been the demo in which we showed you the various steps that you have to go through when you work on Project 7. So to recap, in this project, and in this module as well, we began developing a VM translator. In Project 7, we are focusing only on the arithmetic logical commands and the memory access commands. So we developed a program which is capable of translating these commands into machine-level instructions that carry out the same thing on the host platform. And in the next module, and in Project 8, we're going to complete the VM translator by extending the VM translator to handle also the branching commands and the function and return commands. And by doing this, we'll have a full-scale VM translator which will serve as the back end of our JEC compiler, the program that enables us to write high-level programs and translate them all the way down to machine language. So this is basically the end of the operational part of Module 1. And in the last and final unit, we'll discuss some perspectives and observations about the general notion of virtual machines. Welcome to the last unit of the first module in Nento Tetris Part 2. When we designed this course, Noam and I decided that each module in the course will end with what we call a perspectives unit. This concluding unit has several purposes. First of all, we wish to use this unit in order to say a few words about all sorts of things that we left out from the discussion. For example, if we decided not to deal with efficiency, we'd like to put it on the table explicitly. And we do this because we feel that it's important to not only celebrate what we did do in our projects and modules, but also to acknowledge what was left out and what is very important to include if we want to turn this, let's say, into a commercial product. And another purpose of the perspective units is to provide a historical context and to connect what we do in Nento Tetris to all sorts of well-known hardware and software concepts that you may be familiar with, and if not, we will introduce them to you during these units. And this will help you appreciate the fact that what we do in Nento Tetris has not only a very exciting historical legacy, but also far-reaching practical implications. As you probably saw, Nento Tetris is a nitty-gritty course in which you have to work and develop stuff all the time, and we want to use these units to take a break from the trenches and the salt mines, to get out, breathe some air, understand where we're coming from, where we're going to, and connect what we do once again to our environment. Now, these perspective units are going to be question-driven. That is, we will read 2 or 3 questions that typically come up from learners when we teach these modules, and we'll try to answer them. So let's see, what is the first question? You mentioned that the VM is a rather old idea. How old is it? Well, as you may know, the personal computer era began in full swing in the late 1970s. And this happened when both Apple and IBM introduced to the market 2 personal computers that very quickly became widely popular. And this happened when both full swing in the late 1970s. And this happened when both Apple and IBM introduced to the market 2 personal computers that very quickly became widely popular. These early PCs came out with almost no software on them. Now, during the same period, there was a programming language called Pascal, which was quite popular, but it ran only on mainframe and what was known as mini computers. So people began to develop Pascal compilers for the new lines of IBM and Apple PCs. However, these machines used different processors, different chipsets, and different operating systems. And therefore, different Pascal compilers had to be developed. So if you were a software developer back then, and you wanted your accounting software or your computer game that you developed to run on every PC out there, well, you had to use different compilers, and you had to maintain and support multiple versions of your software. And clearly, this led to numerous headaches and bugs and complaints and developer frustration. Also, IBM and Apple were rival companies, and they had no interest whatsoever to help developers port their software to the other machine. Now, in order to deal with this cross-platform challenge and frustration at the right level, which is the infrastructure level, several researchers and practitioners began to toy with and specify an early virtual machine architecture and language which was called P-code. This P-code, just like our own VM language, was based on a stack machine abstraction. So in order to realize this abstraction on both IBM and Apple computers, the P-code language was implemented on both lines of these machines. One implementation was designed to translate P-code programs into the Intel x86 instruction set, which was used by the CPUs of IBM PCs, and another implementation translated the very same P-code programs into the Motorola 68000 instruction set, which was the CPU which was used by Apple computers back then. So you see that the whole concept was very similar to our own VM language and VM translator. The basic idea is to create a cool processing abstraction, a virtual machine, and then to realize it on as many hardware platforms as we want. In our course, we do it on the Hack platform. So following these P-code implementations back in the 1970s, actually it was already in the beginning of the 1980s, other people went on to develop Pascal compilers that generated P-code instead of machine language. And so for the first time, the same Pascal program, whether it was a computer game or whatever, the same program could run as is on both IBM and Apple machines, each using its own platform-specific P-code implementation. Of course, this whole scheme was based on the assumption that the customer's computer would be equipped with a suitable client-based P-code implementation. And indeed, during this time, these P-code implementations were widely distributed and freely over the internet. So many people downloaded them and installed them on their computers, so the whole scheme worked very nicely. So historically, this was perhaps the first time that the notion of a high-level language began to realize its full potential in a world consisting of different hardware platforms and different machine languages. And you can see how the notion of an abstract virtual machine played such a central and sort of overarching role in this cross-platform vision. Now, in particular, the VM language or the VM architecture provides an intermediate architecture or intermediate layer that hides all the gory, not all, but most of the gory details of the target hardware from the high-level language. And this will become critically important when we set out to develop a compiler in this course later on in some of the future modules. All right, so this was a long answer on the first question. And the second question is, how close is our VM to Java's JVM? So let's see. Java's virtual machine is also based on an intermediate language, which in the Java case is called bytecode. And obviously, there are quite a few technical differences between our VM language and this bytecode. For example, our language recognizes only one data type, a 16-bit integer, and yet Java's bytecode commands are designed to manipulate integers, floating point, double precision, and all sorts of other additional data types. So in that respect, it's much richer than our own VM language. Also, Java's bytecode offers all sorts of high-level abstractions that our VM language lacks, like multiplication and division, as well as low-level commands like bitwise operations and so on. So, it has more expressive power. And yet, in its most essential elements, these two languages are quite similar. Both languages are stack-based, both use push and pop, and both access their memory using virtual memory segments instead of symbolic variables. Now, it may be interesting to track the historical motivation for founding the Java language on a two-tier compilation model, one that uses a virtual machine as an intermediate layer. Well, you see, Java was developed in the mid-1990s by people who worked in a mighty company called Sun Microsystems. And I kind of chuckle when I mention Sun, because when I was at your average age, Sun was a revered company, and now it's no more. Well, actually, it is buried somewhere in the bowels of Oracle, who acquired Sun, very wisely, I think, back in 2010. But going back to the mid-90s, when the story of Java began, the world of business and office applications was completely dominated by a company called Microsoft. And Sun, which was the arch rival of Microsoft, wanted to distinguish itself by dominating everything else. And in order to achieve this dominance, Sun decided to create a new programming language in which one could write programs that will travel through the internet and execute on any possible mobile device and digital appliance out there, whether it is a PC, a digital television, a refrigerator, a washing machine, a sprinkler system, a toaster, whatever. Sun wanted to connect everything, and it wanted everything to be connected to Sun. And so they decided to base this vision on a universal VM architecture that could be implemented with relative ease on any given hardware platform and digital device out there. Now, if the whole thing sounds to you quite similar to P-code, then you're absolutely right. It was the same problem, cross-platform compatibility, and the same VM solution approach, only on a much bigger, world-class, megalomanic scale. So the basic idea, which still prevails, is that a Java compiler first generates bytecode, and this bytecode can be deployed through the internet to any connected device. And once it reaches its destination, there will be a client-side JVM, or a VM implementation, that executes the code on the client device. How? By translating the VM code into the device's machine language, just like we did with our own VM translator. Now, going back to the mid-90s, it turns out that historically, these lofty ideas of Sun were ahead of their time, and the beginning of Java was somewhat sluggish. But then something completely unexpected happened. The cell phone happened. And before you could say iPhone or Samsung, the world was flooded by numerous cell phone models using dozens of different processors, chipsets, and operating systems. So all of a sudden, the prescient Java vision of running the same software on many different devices became extremely relevant. And it happened in a new hardware platform and digital device out there. Now, if the whole thing sounds to you quite similar to P-code, then you're absolutely right. It was the same problem, cross-platform compatibility, and the same VM solution approach, only on a much bigger, world-class, megalomanic scale. So the basic idea, which still prevails, is that a Java compiler first generates bytecode, and this bytecode can be deployed through the internet to any connected device. And once it reaches its destination, there will be a client-side JVM, or a VM implementation, that executes the code on the client device. How? By translating the VM code into the device's machine language, just like we did with our own VM translator. Now, going back to the mid-90s, it turns out that historically, these lofty ideas of Sun were ahead of their time, and the beginning of Java was somewhat sluggish. But then something completely unexpected happened, or a VM implementation that executes the code on the client device. How? By translating the VM code into the device's machine language, just like we did with our own VM translator. Now, going back to the mid-90s, it turns out that historically, these lofty ideas of Sun were ahead of their time, and the beginning of Java was somewhat sluggish. But then something completely unexpected happened. The cell phone happened. And before you could say iPhone or Samsung, the world was flooded by numerous cell phone models using dozens of different processors, chipsets, and operating systems. So all of a sudden, the prescient Java vision of running the same software on many different devices became extremely relevant. And it happened in a new setting, cell phones, something that neither Sun nor Microsoft nor Intel could possibly imagine. So with a delay of about 10 years, Java all of a sudden became the right thing in the right time. And so there's no wonder that it also quickly became the language of choice for developing apps for mobile devices. And up until now, I think that Java is still the most popular programming language in the Android space. So all this goes to show that if you come up with an elegant and clean idea, in our case, an abstract, hardware-independent virtual machine, then someone at some point will pick up this idea, either you or someone else, and turn it into an extremely useful and practical technology. Nothing can stop a good idea. It has a life of its own. All right, now I would like to conclude this module with a note about efficiency. Throughout this module, our contract called for developing a VM translator without requiring that the generated machine code will be either compact or efficient. Obviously, this is a very serious oversight, because you see, you have to realize that technology. Nothing can stop a good idea. It has a life of its own. All right, now I would like to conclude this module with a note about efficiency. Throughout this module, our contract called for developing a VM translator without requiring that the generated machine code will be either compact or efficient. Obviously, this is a very serious oversight because you see, you have to realize that a VM translator is a mission-critical program. It's a program that in one way or another lies in the very core of most PCs, tablets, and cell phones out there. And it may be called JVM or KVM or ART or CLR. At the end of the day, it's a VM translator. And therefore, if your VM translator generates inefficient and lengthy code, then all the apps that run on top of it will become sluggish and users will get frustrated. So in reality, developers of VM translators work very hard to generate low-level code which is as tight and efficient as possible. And that's something that up until now in Nano Tetris Part 2 we've completely ignored. Also, I would like to point out that the stack architecture that we use so carefully in this course is not really a necessary ingredient of a virtual machine. For example, the JVM, which is installed these days on Android devices, uses another abstract architecture which is called register machine. This register machine is perhaps less elegant than Node. Also, I would like of VM translators work very hard to generate low-level code which is as tight and efficient as possible. And that's something that up until now in Nano Tetris Part 2 we've completely ignored. Also, I would like to point out that the stack architecture that we use so carefully in this course is not really a necessary ingredient of a virtual machine. For example, the JVM, which is installed these days on Android devices, uses another abstract architecture which is called register machine. This register machine is perhaps less elegant and beautiful than our own stack architecture, but arguably it generates code which is better optimized for processors of mobile devices. You see, when it comes to efficiency, developers of mission-critical software layers are very opportunistic and they use anything that works better and faster. So we can go on and on with these questions and discussions, and there's no one around here to tell me to shut up. So I'm going to force myself to stop, and we'll meet again in the next module in which we'll continue to develop our VM abstraction and implementation, and this will be Module 2. Is on Android devices, uses another abstract architecture which is called work very hard to generate low-level code which is as tight and efficient as possible. And that's something that up until now in Nano Tetris Part 2 we've completely ignored. Also, I would like to point out that the stack architecture that we use so carefully in this course is not really a necessary ingredient of a virtual machine. For example, the JVM, which is installed these days on Android devices, uses another abstract architecture which is called register machine. This register machine is perhaps less elegant and beautiful than our own stack architecture, but arguably it generates code which is better optimized for processors of mobile devices. You see, when it comes to efficiency, developers of mission-critical software layers are very opportunistic and they use anything that works better and faster. So we can go on and on with these questions and discussions, and there's no one around here to tell me to shut up. So I'm going to force myself to stop, and we'll meet again in the next module in which we'll continue to develop our VM abstraction and implementation, and this will be Module 2.
Vamos a darle.
execute on the and all right, so the next thing that you have to do, once you understand what the VM program is doing, I call the function return. This is the program that we have that encode. You can do it using explain later on. To the overall picture, we can once again is to write a program project 7 as well, standalone to you, and we use it actually important file in this basic test directory. So now the next thing that I learned what it is designed to do, which contains then it a particular created for this handle each so on name of the file, and it goes on to open it. Then there's a constant, and once again other methods in our API will use the at take everyone we assumed, and therefore the stack point one way to equals m, but we don't care about it. We just stream of VM commands, of which push constant I represent that goes from the left to the right. This constant down the road. Then there are two methods called arg1 and arg2 to see exact description of these methods have to return. And you can read the specification to see exactly the arguments of the current command, and you can read the specification to see exactly what these methods have to return. So this completes the description of the parser API. Moving along, here's the code writer of these methods have to return. You can read the specification to see exactly down the road. Then there are two methods called arg1 and arg2. Of these command types, the command type method returns a constant, and once once again, other methods in our API will use this constant down the road. Then responsible for that implements the command, which is the parameter of this to be done with this particular method. And the next method, write push pop, is also a heavyweight method because based on whether you have a push, a pop, and the segment and the index, you have to generate assembly code that implements. What we gave here is we have described the implementation of a VM translator that can handle the arithmetic logic and the memory access commands, and what remains to be done. So, as usual, a module particular class. Now, we'll have depends on extension. And if this were Windows, we'd probably do this. VM translator is all about, and the push constant 7. ask who will develop how we accomplish that, how we started with the device. Don't worry about it. Computer science. Both of you are thinking creatures. Implement it and make it work. Focus on what we're doing now in sort of 100% operations. We'll put in X the value of 17 plus 9. Push Y, the stack grows. We then push 9, the stack. So to recap what we've done so far, and the stack machine will end up computing the value that you wanted to compute in the high level. About later on in the course. Now let's focus. Now I want you to notice that something kind of gets lost in the translation. If we look at the high level, we know from our experience and from our knowledge of the high level syntax of this language is that different variables are static, which is unique to our language. And they're present with some value identical to the previous one, except that the only way to move values from one segment to another in our VM abstraction. So to recap, here again is our VM language. In the previous final stack machine state. Step will be relatively simple. So when we say the P, we imply an indirect addressing operation. So we look at the selected register, which in the Hack assembly language is represented by the letter M. And therefore, when we next say D equals M, we're going to get the value of this register, the current instance of the RAM in 256. Here's another sort of final example, which is kind of symmetric. Here we do something that looks strange. We do *Q equals. So I wish to once again emphasize that what we saw in this example so far is sort of high level, or I call it pseudo assembly code. And in order to actually implement it, you have to take every one of these instructions, pseudo instructions, and rewrite them in your assembly language. If you use the Hack computer, you have to write the code in the Hack instructions in physical memory. And 5 will be mapped on the RAM beginning in address 256 as we assumed, commands that will actually make this transformation. To remind you that if you don't understand this code,
Bueno chicos, es todo por hoy. Mañana seguimos. Tengan buenas noches.